Robin Morris, convener of the Oxford Energy Network, and thank you very much for joining us. Perhaps like me, you're still reeling from the harsh reality we heard last time from Gillian Cooper of the cost of regulatory shortcomings for residential energy supply in Britain. So we'll be seeing that in our bills quite shortly. But this week I have the pleasure to introduce Calliope Panoutsou, Senior Research Fellow at the Centre for Environmental Policy at Imperial College. Excuse me. She's Chair of Biomass Availability and Supply in the European Technology and Innovation Platform for Bioenergy, and is a member of the Scientific Committee of the Bio-Based Industries Joint Undertaking. She integrates natural sciences and economic, socio-economic approaches and policy analysis, and is currently leading research into how biomass can be integrated into climate and energy policies through the European Green Deal. And when thinking about bioenergy as a resource, I look back through some old commentaries from 2018, not that long ago now, but I was interested to see that the International Energy Agency at that point were forecasting that bioenergy would be the fastest growing renewable resource between 2018 and 2023. So maybe we'll hear a little whether that has lived up to its promise. But the sobering thought for me at the time that bioenergy in 2018 already represented around 50% of the share of the world's renewable consumption at that point. Clearly a lot of that is local traditional use of biomass, but it's still a sobering thought that with all the investment in wind and solar photovoltaics, we still do rely on biomass to a great extent. So let me open up the floor to Calliope to hear more about the availability of sustainable biomass in Europe. Over to you.
Hello, good afternoon. Thank you very, very much for inviting me to your seminars. My name is Calliope Panoutsou. I work at Imperial and I have been working for biomass, bioenergy, biofuels and bioeconomy for many years, trying to capture the biophysical potential and understand how it can be best fit into the various demands, initially for bioenergy, biofuels, across the demand sectors, working from heat, local heat, small scale, to larger biorefineries, electricity and advanced biofuels, and more recently the potential trade-offs, competition or synergies, which would be the best case, with the bio-based industries coming from plastics, chemicals, pharmaceuticals, and all the trend towards the circular bioeconomy. This afternoon, I will try to present some considerations about the framework conditions around the topic of availability of sustainable biomass. The focus of the results and the data I'm going to present is Europe, but the considerations, of course, are applicable everywhere. And I will also illustrate some findings within this context from a recent study we participated to for the European Refiners Association in Power. Let me see. So I will present the context and the drivers, how biomass can fit into sustainable futures, information about assessing sustainable biomass supply, so what lies behind the numbers and what numbers are currently projected for supply and how do they actually fit towards the projected demand from IEA and from other sources, and some conclusions on the way forward. So sustainable biomass supply, especially the word sustainable, has been highly debated recently. There are stakeholders and people and researchers that believe and have proven that biomass can deliver a range of products and raw materials and services like energy, which means it can boost economic growth and rural development because biomass is bottom up, it's being produced and used. So this means that it will improve and increase the income of the suppliers, farm income, foresters' income. But there are serious concerns about the risks of biomass provision, and these are focused mostly on the unsustainable practices, which we have all experienced and probably are going on as we speak, for producing, sourcing biomass, but also using it, meaning that if it is supplied unsustainably, it can not respect the planetary boundaries and can have serious impacts on land use chains and water. The presentation, as I mentioned, discusses the availability of sustainable non-food biomass in Europe and presents the projections for 2030. And it also tries to outline conditions and assumptions around the calculation and around the sustainability problems that or risks that one has to take into account when assessing potentials for biomass. The drivers for biomass, as mentioned, it goes beyond energy, and so far we all know that construction materials, feed, food, fiber, furniture, textiles are expected to grow, so they will use biomass, and these are the classic uses for biomass that will increase, but also there's high innovation going into this area, and we will see more and more bio-based chemicals, bio-based plastics, lubricants, etc. These are being brought forward fastly because they can offer a higher added value per mass unit of biomass used. But alongside these uses, there's also the energy. And despite the high aspirations and projections about electrification of many sectors, it is acknowledged by all researchers and policy and industry that electrification alone cannot be a silver bullet. Certainly cannot be an immediate silver bullet. There's a transition period towards a low carbon net zero. And despite the impressive potential of other renewable sources, biomass will be there to provide grid balancing, to help difficult to decarbonize sectors make their transition towards decarbonization, meaning aviation, heavy duty, maritime. And this means that there are complementary roles for bioenergy and for electricity from renewables until 2050 at least. Moreover, biomass, because it is a local resource, can deliver social resilience. And this means there will be locally produced biomass, which has to be collected, transported, densified. And this means that in periods of energy, or even used for heat and for transport, this means that in periods with high energy bills and energy regions that are going through energy poverty, high energy poverty risks, biomass can offer a high service as well in terms of stabilizing the fluctuations of the energy prices and the fuel supply for communities that are not so fortunate to be able to afford the high energy bills that are coming or are about to reach us. But biomass has to be sustainable. Again, sustainability has been and is a serious concern in any development projection, political target. Biomass is a natural resource. So whether it's for food or whether it's for raw materials, the provision, it is within the provision of ecosystem services. It can grow and it can regenerate. So it's not a finite resource, but it uses resources such as land and water. So the availability and the provision of biomass has to be subject to safe operations. And these have to respect the planetary boundaries, such as land, water, and other resources. But at the same time, can also provide the social welfare we mentioned. And for this issue, sustainability criteria are there and can deliver a commonly accepted framework for biomass provision. Biomass, the non-food potential, is diverse. We're talking about residues from several operations on field or in industries, from forestry, from agriculture. We're talking about the organic fraction of municipal waste. And we're talking about broadening this supply within sustainable boundaries. This means there are elements of increasing yields and using varieties that are better adapted to local ecosystems, introducing different cropping practices, rotations, cover crops, which can also facilitate the protection of soil erosion in sensitive areas. And more and more we hear about carbon farming practices, which mean the practices of cultivation that include conservation tillage, include rotation, agroforestry, anything that can improve the soil quality and maintain and increase stores of carbon in the soil. And an additional resource that is on the research element and also now is slowly becoming the target of future policy is the cultivation in degraded, in marginal land, meaning land that it is unused for many years, has been abandoned because it's not profitable, and is degraded or contaminated. Of course, this land has severe constraints sometimes, and it is very difficult to cultivate, but there are times that it can be cultivated and it can be improved with the addition of biochar, with the addition of different elements, and it can be restored and brought into a productive state. So what comes into the assessment of sustainable non-food biomass supply? This is just an illustration of work we have done with colleagues within Imperial and different institutes. How we bring together data sources and different types of modeling. Of course, this is an example. There are several models and several ways to go. But the critical point is to understand your baseline. And as baseline, it's important to understand the supply streams and the demand streams. And it's important to know from the large data sets that are consistent what type of projections in the cultivation of crop and in the market demand are there. And the same, of course, with the different forest resources. And when it comes to crops, there are crop growth models that can project the growth and the production under different climate features and risks. And on top of that, we work with different colleagues around Europe and internationally that are cultivating the sort of called dedicated non-food crops. And we take data for the input they need, their yields, the actual yields from the field trials or the demonstration trials, and we try to validate any type of modeling. And all the supply and demand data sets are being coupled with the greenhouse gas and carbon projections for savings and balances, and also with costs. Sorry. And this means you have the overall picture of the biophysical potential and also the environmental implications and the cost implications, and you can work with assumptions in the form of scenarios of what impact different sustainability criteria or resource efficiency footprints or different policy interventions will have towards the evolution of the biomass potential as it is right now. With this, you can have outputs like the projections of the biomass shares in a given time frame, in a given sector, like electricity or heat, or for advanced biofuels, or for bio-based economy. You can understand and quantify the impacts and appreciate the mitigation options and validate them. As such, you can provide informed evidence towards different policy interventions or different exercises for setting and validating policy targets. Some of the framework conditions that are very closely related to the biomass availability, but also to the climate impacts, have to do with land availability. There is extensive research and policy around the issue of land use change, or indirect or direct land use change. There is intense activity at the moment for sustainable carbon cycles within the agronomic practices, different species and how they fit to land use and also to the carbon cycles. Water management, depending on which part of this planet you are. There are areas that are facing desertification and climate change impacts that lead to high temperatures and during a long period around the year, and also dryness. So their cropping is about to change and their yields are at risk if they don't irrigate. As I mentioned, the greenhouse gas emissions and the carbon debt, especially within the forest management, issues of biodiversity, and as I mentioned, biomass is within the provisioning of the ecosystem services. So, and it is not only for energy or only for fuel, so it has to be considered within the overall ecosystem services of a forest or of a net or of a field of the whole area. When it goes to carbon, it's acknowledged that biomass is a specific carbon stock, includes carbon stocks in the vegetation and the soil, and it is considered a natural reservoir of carbon that's sequestered from the atmosphere. It can be harvested and used for a range of products, but slowly, policy is oriented towards prioritizing products based on their long life in terms of sequestering the carbon and being transferring the reservoir of the biomass into the product itself. With this way, for example, introducing more wood into buildings that are going to last for many years is more important than burning wood for energy. Although, again, the lifetime of these products has an end, some of them, as I mentioned, are long-lived, and they can still keep the carbon and retain the carbon stocks and are considered carbon sinks. Of course, there are cases, and this goes upon the time, the scale, the region, the value chain that is addressed, where biomass can substitute the fossil, high greenhouse gas intensive materials and energy. There are situations where having such systems that have low greenhouse gas emissions in combination with carbon capture and storage can contribute towards negative emissions. Again, as I mentioned, when it goes to agriculture, carbon farming is a set of practices that is being brought forward fast, also for policy. It facilitates the carbon sequestration and improvements into the soil, improving their structure, the capacity to retain the nutrients, the reduction of erosion, increasing soil moisture, and as such it recycles all the nutrients, helps all the nutrients and helps having a better and healthier soil, which means you have a higher yielding crop and the system is functioning much better. It is the same for the farmers. They, by applying carbon farming practices, they can improve soil quality, they can reduce the risks of having soil erosion, they can cultivate more crops better, so they have they maintain their biodiversity, and also it's not widely applied at the moment, but soon there will be carbon credits that they can benefit from when they have carbon farming practices in their farms. And of course, biodiversity within the assessments of biomass. It's important not to consider land that is of high and significant biodiversity. These are areas that are already designated as high nature value, Natura, etc. On top of that, the land management practices have to be accounted within the context of not harming biodiversity, meaning the use of domestic species and local varieties, avoiding monocultures, avoiding invasive species, trying to mix annual with perennial crops, try to apply intercropping, and use methods that are of low soil compaction, which means machinery, not heavy machinery, not intense fertilizing, pesticides and chemical use, and avoid as much as possible or use efficient modes of irrigation. Again, there are different combinations of biomass-based mitigation options for climate change. This is just a figure that was very illustrative from the IPCC, where you can see clearly the different impacts of bioenergy with bio-CCS and reforestation, afforestation, and biochar addition to the soil. All these impacts have impacts for mitigation, adaptation, desertification, land degradation, and food security. All of them are positive for mitigation and adaptation, but when it goes to also securing food, we see that the reforestation and forest restoration helps food security, because you restoring more forest and using land that cannot be used for food, you allow larger resources for land resources for food and feed. And the same comes to biochar addition into soil, because it tackles the element of marginal land or degraded land, and it improves it. And then it reduces competition for land with high quality. And some results. There are different studies, different ranges for biomass potentials. Here I just illustrate a few of our review work and recent work. In general, within the years there have been several biomass studies, but it's the science and the modeling and the integration of the modeling, combining land use modeling with energy modeling and economic modeling and climate change projections. We come into projections for the European Union and Europe, the wider Europe, that are the high projections are above 1 billion tons per year. Of course, when you go into scenarios and here I will explain in the later slides a lot more. We have low and high projections from 3 very recent studies. What drives the ranges are different yields and yield improvements because of better practices and the use of better machinery. Of course, improved local knowledge. There are areas in Europe that there's a lot of knowledge on how to harvest, on which machinery to use, when to do it, what varieties. There are other areas that these things, knowledge is lagging behind. And of course, there's a lot going on in terms of the technological improvement, and this innovation drives improved technological readiness level, and this also increases the yield. Another element when you try to match supply and demand is the prioritization. Try to understand, based on the new technology and the innovation that is coming in, how technological maturity in combination of market readiness can help prioritizing the different resources. And this is just a slide illustrating the case for advanced biofuels who have multiple options of raw materials and conversion pathways, but only a few of them are commercial and some are coming, like lignocellulosic with bioenzymatic hydrolysis and fermentation to ethanol. But there are also some others that gasification or pyrolysis that are still lagging behind. So when you prioritize the use of biomass towards 2050 the decarbonization, it's not only enough to know how much supply you could have or the range of sustainable biomass, but it's also important to understand what are the conditions for supplying this biomass into the different sectors based on their technological maturity and as they evolve in the transition to net zero. I have shown before the projections that this was in million dry tons. Here I just will illustrate the demand supply. So here you see million tons of oil equivalent, and the biomass supply comes from these 3 studies. The recent one we have done, the one that has been performed by a group of colleagues in 2017 for the European Commission for Research and Innovation, and the one from JRC for their energy model, the TIMES model. So the projections from IEA and also from JRC were for something around 200 MTOE, a little bit less in 2030. These were the projections for the consumption, and you can see that the range from the low supply, the assessment for the availability is 190 to 2008 in the 3 recent studies. The studies, I forgot to mention, are using the same baseline data sets, so they have a consistency in the basic data sets they are using, but they have different scenarios and they differ in the baseline year. So they have a consistent data set behind them in terms of before assessing the biomass supply. The higher level is 262 to 434 million tons of oil equivalent. So basically, till 2030, biomass, sustainable biomass for bioenergy, which includes biofuels, can be available, and the targets of the projected consumption can be met. The results as we go to 2050 are roughly similar. Of course, as we go away to 2050, there are more assumptions, so there is a larger modeling divergence. So here we see that the low scenarios of the 3 studies do not reach the higher projected consumption of 250 MTOE. They reach maximum to 224, but the high scenarios exceed almost double So this is a slide just to put in context how the projections for supply and the projection for the bioenergy consumption fit together. Because sometimes there are these questions of how these two can actually inform each other, because most of the modeling for the consumption is not done together with the modeling for the supply. When it goes, I will just add a few slides here about the considerations this is for sustainability in the different segments of biomass, so biomass from agriculture, biomass from forestry, and biomass from waste. When we're talking about biomass, the non-food part from agriculture, we're talking about residues like straw, prunings, agro-industrial residues. And here there are different methodologies to use, but basically you have the land use, the crop yield, the residue to product ratio, and then you have a theoretical potential of what a hectare of land can produce. Then you have technical limitations of how much can you harvest, what machinery you have, what climate and soil conditions, and then you have a technical potential, but then you apply the sustainable removal rates that take into account, as I mentioned, soil biodiversity, water availability. The considerations for the field residues, agricultural residues for sustainability are that there are certain levels of soil organic carbon and nutrients that need to be considered, because if you exceed these levels, you are at risk if you remove higher amount of residues. And for the agro-industrial residues, there may be competition with animal feed. So these things need to be considered when somebody assesses the biomass supply. Again, here is just a zoom to the organic, the soil carbon. It's important. This is a study from 2015, but it was with consistent data sets and very detailed. So it shows in the red, it shows the areas where 50% and higher straw removal risks soil carbon, and in the blue it shows that you can harvest more than 50% without risking soil carbon. Again, here are some more details about the assessment of prunings and cuttings. I won't stay in this, the presentation will be available. And here is from our recent study. It is just an illustration of the concentration of the different agricultural feedstocks. Here you have the field residues from cereals, from maize, from agricultural prunings and oil crop residues. And you can see the concentration in the center of Europe for France, for Germany. And here you see the agro-industrial residues. And these are again from the recent study we participated. And these are the potentials from agriculture. Again, this is agricultural residues from field cereal, straw, prunings, manure, maize, stover, oil crops, and secondary from the agro-industries. And the range was from 275 to 370 million tons, dry million tons per year. Again, this is agricultural biomass for all markets. This is what can be sustainably produced. And this is one of the scenarios. The numbers are from one scenario, but this is mostly to show you which countries hold the highest concentration of these potentials. And you see France, Germany, Poland, Spain, Romania, Italy, Hungary, Bulgaria. The UK also appears in the higher shares. In this study, in the recent study we have done for Concave, we framed the potential, the overall potential with specific key assumptions to estimate the potential for bioenergy. So we have three scenarios, a low, medium, and high, and we have considered different removal rates of field residues based on the different literature, and also of with interviews with people that are working with straw removal. Same for the use of pruning and the yield increases in crops in unused, degraded and abandoned land. And we have also framed the use of such land, the marginal land. The low scenario assumes that only 25% of this land can be available. We go in the medium scenario 50, and the high scenario we assume that only 75% of this land will be available, because this is land again with severe, sometimes biophysical constraints, and it may take time, or it may not be possible to restore. So once all these considerations are taken into account, again, this is the regional distribution, it's the same. The potential is reduced, and for bioenergy, we have estimated 230 to 320 million tons. This is a reduction because of the demand for bio-based materials that is projected so far for 2030 and for 2050. When it goes to lignocellulosic crops, we have used in our study a mix of perennial and short rotation copies, and also a couple of annuals. I will show them after, but the main sustainability issues are they have to be integrated, and this means that they have to be integrated with the current habitats, and you have to avoid land use change, direct or indirect, and also avoid monocultures and avoid harming biodiversity within the region. And these crops are expected to go into land that is on risk of abandonment. Here we see in a map which is recently produced by the Joint Research Centre the risks of abandonment by 2030. By red, there are not many red, but you can see a lot of orange or a lighter orange around Europe. And these are areas that are slowly being abandoned, which means they will be marginal, and if they are left, they can be also degraded. And using them for dedicated cropping, like the lignocellulosic crops, would be a good thing to keep them and restore them and increase their soil carbon retention. On the left, you can see some figures on average from 20 studies, and in green one we have performed a couple of years ago. The estimated area of marginal land ranges from 8 million to 40 million plus. Our recent estimates, which also have graded this area in low quality marginal land, which is the most the one with heavier biophysical constraints, is roughly 25, and there is another 10 for high quality, which is the land that's been abandoned for socioeconomic reasons, because it's been cultivated, but it is uneconomic, so it's easier to bring back to the production. And here's the estimates of how this land, the low quality on the left and the high quality of land on the right, of land that can potentially be available for lignocellulosic crops by 2050. And here are the assumptions for the yield potential. We have used very modest yields, and we have based them again on a review of different studies and research, but also on discussions and interviews with colleagues that cultivate crops in marginal land. As you understand, this is a scenario-based potential with the yield, so any yield improvement always brings more potential. And here's again for information, again, it will be available, the set of crops we have used, and it's a mix of annual and perennial. We tried to introduce an establishment and a harvest that are not the same for all the crops, and different soil types and different adaptation to climatic conditions around Europe. So again, the potential calculated, this is the original, you can see Spain, Poland, Romania, Ireland, France and Germany having the highest shares of marginal land, and it's from 36 to 127 million tons, depending on whether you are in the low scenario, which is 25% with low yields, or where you are in the high scenario with high yields. Again, when we go to forest biomass, I won't stay on the definitions, but they are very important because biomass is diverse, and it's important to be clear on what you include and what you don't include. So there's a part of biomass from forests that can come from stem wood, from logging residues, and from the stumps that are when the whole trees are extracted. But also similarly to agriculture, there are forest industries where you have bark, and also you have wood processing industrial byproducts. Again, when it goes to sustainability, the field forest residues, there are issues of soil quality loss, biodiversity and carbon debt when you remove the whole quantity of the residue. So there are annual harvest increments that are clearly set within the forest management plans for every country, and take into account the different forest ecosystems, the climate change projections. So they are very well regulated forests in most of the countries. And when we go again to the industrial residues, here you have competitions not with animal food and feed, but there are different material and bio-based material and construction and textiles that are in competition with energy and with fuels. Again, here is the spread of the different types: stem wood, primary forest residues, and the secondary forest residues. And the potential we estimated from forestry for all the markets ranges from 550 to 720. Of course, as expected, Scandinavia, Sweden, Finland, and also UK, France, Germany, and Poland, with Austria and Italy and Romania coming afterwards, hold the highest shares because they are more forested. To evaluate the potential for energy, we took into account some considerations. Again, the stem wood for energy, which is called fuel wood, at the moment there's a 45% that is being used. In our low scenario, we assumed 25% that this is reduced because of the current debate about the carbon sequestration and carbon debt, so that forestry and especially stem wood is very likely and will be directed to products with longer life, such as the construction, and not to energy. So we restricted both the medium and the low scenarios to range to percentages that are lower than the current traditional shares, and we have kept the high scenario slightly above what is happening at 50%. And then similarly, we have capped the primary forest and secondary forest residues availability. And here is the, again, these are the assumptions for fuel wood, the 25, 30 and the high 50. So the forest biomass potential for bioenergy reaches to 200 to 400 million dry tons from the overall. And when it goes to bio-wastes, we have used the common terminology of the waste directive, but which is tied to the nomenclature of economic activities, the NACE waste categories. And we have included in the study common sludges, municipal waste, fats, used fats and oils, household waste, animal mixed food, vegetal waste, wood waste and paper. And we have been calculating these and the projections over the years based on population growth and gross domestic product growth rate based on Eurostat projections. Again, the assumptions are that we will have in the low scenario 60% of bio-waste recycled and 40% available for energy, and in the high scenario reverse 40% recycled and 60% for bioenergy. The 50-50 scenario is close to what the waste directive projects, but we see the bio-waste availability for energy being reduced, mainly because of the trend that bio-wastes are going to be waste generation is going to be reduced also because of behavioral change of wasting less. So there will be, not only because of the recycling, but also as a society we move towards lower waste patterns, hopefully. Here's again the potential in M2E at the moment. So you see it's not so much, it's 15 to roughly 24, and we see countries, of course, with higher population and higher economic activities like Germany, France, Italy, the UK, Spain, having the higher potentials. So these were, I hope they were not very tiring. These were figures from our study and other different studies and how supply and demand can be together. And here are some conclusions and some suggestions for way forward on what is going on. Bioenergy value chains are complex, so their efficiency and resilience has to be optimized. It's very clear that there's competition from other industries, so and this has to be reduced and more synergies have to be promoted. So clear policy focus is essential to improve the performance in a sustainable manner. And this dictates that policy and industry and also the actors, all the key actors involved, have to define their priorities and also quantifying the impacts using the appropriate metrics that can be understood by everybody involved in the value chain. There are several policies in place, but because biomass is diverse at source, so there's a lot of policy that's being formed for agriculture, for forestry, for waste, and these all have to be coordinated. And also on the demand side, there are policies that come from climate change, policies that come from energy, policies that come from transport, from chemicals. So all of these need careful coordination and appropriate integration of the interventions and regulations and financing across the value chain. Again, the bioenergy value chains, as I mentioned, are increasingly varied and innovative. They must have resource efficiency and sustainability. They unfortunately have, because of the diversity and their broad both supply and demand issues, They're complex, and they have, most of the times when you try to do a consistent modeling, you find yourself in open-ended or unrelated metrics and lack of data availability. So you do need a systems perspective and system thinking to understand which stages of the value chains have challenges, what challenges they have, and how you can better address them in an effort to harmonize the value chain, the raw material, and prioritize the end users. This brings research for indicators and methodologies. This helps understanding the energy systems, and this helps model integration, facilitates having open data sets that the models can use and share, and then they can have consistent projections. And this can inform the debate of how sustainable biomass can provide input to low carbon or the transition to net zero. And of course, this has to be done in a technical, on an economic, environmental, and social way. Of course, there are issues for scenario analysis and foresight or forward-looking analysis. We are working with risks and projections, so we need to be aware of different uncertainties that we have to internalize into the projections. This needs to account for all the biomass that can be available, the impacts that the provision may bring, and also on the potential different interests for the demand side. And when performing the policy analysis, it's very important to have the models integrated, so working with land use climate change models and also biophysical capacity models, including the crop growth models, the forest models, but also having econometric models, having models that can account for the whole energy system, and try, I know it sounds wishful thinking and very complicated, but more and more researchers are working together, trying to capture these dynamics and try to understand the potential evolution of the sustainable biomass provision into the different end uses alongside the implications of climate change. And of course, this has been the top-down approach and is very informative. It's relatively closer to policy making because it can have a certain uniformity in the thinking, but there needs to be an element of inclusiveness and involvement of the stakeholders on the ground, where you will actually implement all these let's say aspirations, all these new green biomass systems. So co-creation, involving stakeholders at local level, especially the stakeholders that have less access to knowledge or limited ability to process and understand all these complicated data sets or complicated demand-supply dynamics. So working with people on the ground at local level, at regional level is important. And I hope I have made it in time. As I mentioned, the presentation will be open and available, and I'll be very happy to discuss and have questions.
Thank you very much indeed for that, and thanks for keeping going without any response from the audience while you're speaking. One of the senses that I would feel I'd like to get is for a low value residue that might be in a quite distributed area. Can you comment about the energy cost of gathering together this relatively diffuse resource in order to realise its value? My understanding, even from local thermal generation, if you go more than 20 kilometres away, it's kind of not worth bringing the thing to burn. So could you comment a little about that energy cost, please?
Yes, thanks. That's a very important question. Biomass needs densification. So the way things are proceeding at the moment, progressing, is you do not carry raw biomass in the form of wood chips or only straw, which is not made into pellets or briquettes or something more dense. So having intermediate depot facilities is in the planning of different regional, let's say, local biomass heating, or even the biogas digesters that operate in a smaller scale, and they have to receive manure and probably some sort of cropping. The answer to reducing the costs and improving the energy density is to design the system with intermediate biomass hubs or biomass depot. And this, of course, when you do a cost benefit, defines the scales, and also it may be the case that you can have 2 plants instead of 1, because you can source around them in a more efficient way. Both energy, greenhouse gas saving, because if you transport as well longer distances, there is an element. But this is how this is being addressed. So as you go to larger scale, you store your biomass in a more dense form, or when you go to the chemicals or the fuels, you pre-process and have intermediate carriers that are a lot more energy dense, and carry them. So you carry the oil, or you process it closer to the collection.
Thank you very much indeed for that. We have a question online from Nick Jelly. Nick, I don't know if you'd like to turn your camera on.
Hello, thank you very much for a very interesting talk. I just wonder, to what extent do you feel that biogas from anaerobic digestion could displace the need for natural gas? I mean, I'm sure it will depend on country, but it's been suggested that with the more pasture land becoming available because of the decrease in use of cattle, that we could grow, say, grass and produce much more biogas through anaerobic digestion. What are your thoughts?
Thank you for the question. It's a very important one. I think it certainly can be examined per country, per region, per case, and it is a very good option. There is more and more in countries like Germany, Denmark, the biogas, biomethane, and then injection to the natural gas grid. So, or biomethane for transport, which we see in Scandinavia. This is very important for another reason. You can combine in the digester manure, you can combine grassy or crops that can be digested, like cover crops, which can be, we do not use additional land, and also certain fractions of waste, and that way you can increase your scale and you have a digester. And there are, for example, movements like the Biogas Done Right in Italy, where they recycle, and they have also managed to have favorable regulation and favorable financing within their country, and this model is now gaining attention, this Biogas Done Right model, and it is because it can have complementary resources in a region where you have, as you said, some sort of pasture land, and then you have some agro industries, and you select all the elements of the resources into the digester, and then you scale up.
Great. Yeah, thank you very much. Thanks.
You're welcome.
Thank you for the question, Nick, as well. We've got another question in the room here, and just give me a moment to turn on the other camera.
Thank you. Right, thank you very much. I'm John Rees, by the way, from ECI in Oxford. Thank you very much for giving us a presentation with huge amount of information and ideas, particularly those of us who are not particularly knowledgeable about biomass. I'd just like to ask you one question, and that is, what do you think the, taking a sort of an overall view of the sort of climate challenge, what do you think the big policy interactions are between biomass? What are the really big policy issues? I mean, for example, is it to do whether we go for hydrogen in transport, or biomass as part of the heating, dealing with the heating problem, or biomass as for peak load in power stations? What do you think the big choices are that matter for the future of biomass?
Yeah, well, thanks. That's a very important question as well. Thanks a lot. I think at the moment it is carbon, and in all forms. So it is the policy friction, if I can call it, debate at the moment is let me start from the beginning. 5 years ago, it was land use change. There was this huge debate about finite land resources, and biomass for energy and fuels was distorting the place. So that was the big policy question. Now it is more about carbon and about sequestering carbon, and which end use would be doing that better. And it seems that any long-lived product will be prioritized, meaning the construction and the materials that we can use and reuse. The issue of burning biomass for electricity, heat is a different aspect, especially heat in rural areas, because for heat in urban systems, it goes again to electrification. But biomass for electricity is not an issue anymore. It's not prioritized. It is going to be for products because of the carbon stocks, and it will also be prioritized to sectors that cannot be decarbonized easily because the technology is not yet there. Like the aviation, the maritime, and the heavy duty. But now I think the biggest policy issue is carbon and how to sequester it best.
Thank you very much.
Thank you.
Thank you. So from what you tell me, we should be probably using all of the forestry products just to build and displace concrete or bricks or whatever.
My humble opinion is that there is room for both, for all, and there should be, because for years there has been fuel wood. And we do know that once this is used efficiently, meaning with boilers or stoves that can convert efficiently and also have the environmental standards for the emissions that are strict, then this is something that is a provision of services especially for rural areas. I'm not talking about the pleasure fireplaces in house. This I can understand, and I sympathize, is not best use because it's in an amenity kind of thing. And yes, you can do better, but there will always be a high share of wood and not the high quality wood. There is always the quality element, but the fuel wood that will go for efficient heat. And policy understands that they are not going to take that away. And also an additional element that I would like to mention with the forestry, I didn't add it in the slides, it was too much detail, is that there are some countries that their annual forest harvest management plans reach the annual harvest index, which is from 65 to 80% of your net increment, the growth of the forest. But there are others that do not reach even 50, so there is room for improved harvest. This is one way to broaden the feedstock in the forestry. This will also help the forest regeneration processes, because it will regrow more, you will create more spaces for sunlight, and then it will improve. And also there's a great way that colleagues in Scandinavia are operating their forest management plans. It's the harvesting, rolling harvesting. You don't harvest everything every 5 years. You don't harvest the same diameter of trunks. You prioritize the branches, because that's when you can actually, you have to prune your forest, the trees, and they can grow better. You regenerate your forest, you put it in your forest management plan. So there are all sorts of forest management activities that once implemented, of course it takes time, that's the difficult part with the forest. You need 10 years, 20 years to implement a plan if you don't have it. While with a field of wheat, you can change next year. Agriculture can be faster in these systems, but there will always be ways for improvement in the resource base. And once there are sustainability criteria and monitoring procedures, then the appropriate sustainability criteria is safeguarded.
Thank you, and apologies for turning on the camera a little early. We had another question in the room, so thank you.
Hi there. Thanks for
Hello.
Thank you. My name's Aaron Anstey from Anstey Energy. I've got a question really, just to get an idea of how much land's required. There's Drax Power Station in the UK, which burns, I think it has a capacity for 3 gigawatts of biomass. And just wondering how much land that would require, but also, is that a sustainable kind of model for other power stations to follow, who are perhaps changing from coal to using biomass?
I'm pretty sure they have checked the sustainability restrictions, because that's a big operation. But changing from coal to biomass, it has huge benefits for the emissions. And if this biomass, because it is all relevant to what you substitute, which is the greenhouse gas or the carbon element. And if you make sure your biomass or the crops are integrated and well planned, then and also adding to this, we're working with colleagues from Miscanthus and adding to this the soil carbon and improvement with the practices they do, then you have your soil regeneration, you have your raw material that can go and reduce your fossil needs. So yes, it can be done. As long as there are monitoring procedures that are effective.
I guess the thing we're trying to grasp at here is the scale. Will it cover the whole of England to grow sufficient crops in order to supply a 3 gigawatt generation plant?
Oh yes, when we goes to scale, I'm not quite sure you can grow all that biomass in England.
I think on the flip side of that question, I was going to ask, because I saw someone on the call from the University Estates Office, to what extent could something like a university dedicate a part of its estate to grow some crops in order to reduce its own reliance on more fossil fuel inputs? So So how's that scale? Imperial College or University of Oxford take some of its playing fields or land?
Oh, that would be that would work if it was done on a demonstrative way of also illustrating the regeneration, the ecosystem service provision. That would be a great plan for some of the big names or the big players, because then they are also focal points that attract attention and visibility. So they can act as, let's say, flagship or best practices.
Very interesting.
And they have a lot. They have a lot of science to back it up, and also make the planning in a way that what is shown in them by the models can also be shown on the field.
Well, thank you for taking us through quite a mind-bogglingly wide range of concepts across the whole of the continent of Europe in such a short time.
Thank you, thank you. I hope it wasn't too much, but I'm very happy to reply questions by email as well.
Okay, that's very good of you, thank you. So a quick advert now for the next seminar, which will be in 2 weeks' time, and it will be Charlie Wilson, who's just recently joined us as Professor of Climate Change and Energy, Group Leader at the Environmental Change Institute, and he'll be exploring digitalisation of daily life and the impacts on carbon emissions associated with that. Please remember now to sign up to the Oxford Energy Day, and we very much hope to see you there in person. If you can't make it for whatever reason, it is possible to join online. But thanks again for a very insightful presentation this evening, and I hope you all have a very good evening. Thank you.
Thank you very much. Have a nice evening. Thank you. Goodbye.